I'm Chandan Mishra. I'm engineering manager in Amazon Q developer team. I manage code security engine, and this engine we power the code scanning in the Amazon Q developer, in Code Guru security, and Amazon Inspector. With me, I have Pranav. Pranav here. Yeah. So, so today we are going to talk about how Amazon Q developer helps developer with the code security. And we will talk like how you can build secure application by building code in secure manner. So the presentation will be in the two part. The first part we will talk about the different ways you can make your code secure and what are the features and toolings AWS provide for building secure application. And in the second part, we will deep dive into the architecture of our code scanning engine, and we will end with the presentation. So I will start with the Q developer introduction. Then I will talk about why code security is important in the entire software development lifecycle. I will talk about why shift left security approach is helps developer in building secure application, and what kind of pain points we have seen while talking to customers with the shift left approach and how we are mitigating those. We'll discuss how we are using generative AI to solve the code security problems, and we will have the deep dive into our code scanning engine. In last few years, we have seen that generative AI has changed the way developers build applications. Developers are relying a lot on generative AI applications and tool for writing their code. Generative AI is helping developers as a coding companion. From the Gartner report, by 2026, we expect around 80% of enterprises will be using some form of generative AI applications. At AWS, we feel we can help our customer solving the security issues with different kind of generative AI offering we have built in past. We have built many different products over the last 2 decades, and we not only give this product to our customers, but also we use internally within the Amazon, Alexa, and all the organizations. Last year, we built, we launched like Amazon Bedrock, which helps you to build generative AI applications where you don't have to worry about managing the infrastructure, and Amazon Bedrock takes care of all the infrastructure management for running the large language models. Last year, reInvent, we did the public preview of Amazon Q Developer, and this year we did the GA. Amazon Q Developer is the most capable generative AI assistant. It helps developer with all different type of coding related tasks which they have to perform, whether they are writing code, they are debugging the code, or they want to test it, or they want to upgrade it. It provides all the tools to the developers and the IT professional in building highly available software applications. Security and the privacy we have kept in mind from the beginning while building the Amazon Q Developer. It was not a like afterthought. We want our customer to use generative AI product and services which we are building with confidence that they will be building secure application with the help of Gen AI. So in the code security part, specifically here in Amazon Q Developer, what we have done, we have looked into how generally developers build application. Few years back, most of the code like was written by the developers, but in last few years, what we've seen, developers are relying more and more on the AI companion. AI assisted coding has become a norm, and it helps developer in increasing their productivity. So the first thing which we have done in the Q Developer, we have ensured that the AI, the code which AI is generating is secure and robust. On top of that, what we have done is still, when even if AI is helping you to generate the code, but a lot of code is written by the developer. And many times AI generates the code, but developers modify those. To ensure the code is still secure, we have provided built-in feature in Amazon Q Developer, which helps developer to find and also fix the issues. I will talk about the static application security testing, which is also called SAST. SAST is the branch or a vertical within the application security testing. It helps in identifying and remediating vulnerability into the first-party code. In SAST, we look for different kind of commonly patterns associated with the security vulnerabilities, and we develop rules to detect those issues, and then we also remediate those issues. The benefit of SAST is it improves the overall application security. Fixing issues in the early phases of development is much faster, and it helps in reducing the cost also. Now, when we talk about the code security, let's look into, in general, how developers do the software development. It starts with the design, where developers write a design. Then they write the code in their one of their favorite IDs or code editors. Once they are done with coding and they have done the testing, they send code reviews. Code reviews are reviewed by the senior developers. And once the code reviews are approved, that code gets merged into your code repositories, and also the code goes through the CI/CD pipeline, where the code goes through again the build process, integration tests are run, and then this code gets deployed into different stages. You will have some test stages, gamma, beta, different stages where you will deploy your code. You will ensure the application is running correctly, and at the end, final stage, you will deploy the code into your production stage. Application security is important at every stage of software development lifecycle. I can give few examples. In CI/CD pipeline, if suppose you have a code security issue, you can block the pipeline, you can block the merge. So you can ensure that if developer code review has a critical vulnerability, and you can configure that, you can block the merge. So that way you prevent a critical vulnerability going into your production or getting deployed. You have that flexibility. But when developers want to fix that issue, they have to go back to their ID and they will make the code changes. And now it becomes difficult if they have to come to their code review process to verify whether their fix is working or not. So having a code scanner within the ID helps developer to write the code, verify their code is not having vulnerabilities, and then once they are sure, they can send the code review. This saves a lot of time for the developers. Similarly, for the code repositories and the production application, in ID and CI/CD, only those code changes goes through the security scanning which developers are actively writing. But what about some zero-day vulnerabilities, like log4j happened in 2021? When some zero-day new vulnerability gets detected, it's very difficult to enforce those in the ID or CI/CD because maybe there is no active code changes going on. And there, what AppSec teams want, they want to scan all the code repositories and all the production application to make sure none of those applications are having those critical vulnerability. And that's where the application scan or code repository scan becomes very important. What we have done here, since like I talked about, like every stage of software development lifecycle, you need to make sure your code is secure. So what we have done, we have built a SAST scanner for all these different use cases. Within ID, you can use Amazon Q Developer, which has inbuilt security scanning feature. You can run that, it detects all the security issues, and you can fix those. For the CI/CD and the code pipelines, we have Amazon CodeGuru Security, which supports the SAST scan. And for the applications which are running in your production, we have Amazon Inspector, which looks into your production workload and runs the code security analysis. I will talk about the shift-left security approach. And here, when I say shift-left approach, left is basically in the ID where you start writing the code, and right is the production where you deploy your application, final application. So with shift left security, first thing, let's talk about what is shift left security. Shift left security is the approach where we detect and fix the security issue in the earliest phases of your development, starting from your ID. The vulnerable code gets detected while developers are writing the code rather than in the later stages in your build or release cycle. Developers becomes the first line of defense for your security. And it creates a model where security engineer and developers, they work on a shared responsibility model where security is owned by both developers and security engineers. Now, what is the benefit of shift left security? Why it helps? The benefit is it is very cost effective first, because detecting an issue while coding in the development time is much more cost effective rather than when this issue get deployed into multiple application and you have to go and fix or run some campaign to fix those issues. It takes a lot of time. The second reason is, in any organization, number of security engineers are very less. Typically, we have one security engineer helping almost 100 developers from multiple teams. So what happens, for every application which you want to release or launch to your production, you have to work with your AppSec and security team to make sure that your application is secure, and then only it goes into the production. So if all the security testing, everything, if security engineer need to do, then it takes a lot of time. Shift left approach offload some of those to the developers, where developers make sure before they go for security review, they resolve those issues. And this makes the security review process much faster. And it helps you to deploy or release your features much faster. Now, we talked about the benefit of shift left security and how it helps developer. But it also creates bunch of new pain points it creates for the developers. Now developers need to worry about not only like building the application and releasing at the fast phase, but also to make sure they understand how to solve the security issues. So let's talk about some of those pain points, and I will also talk about how we are helping to mitigate some of those pain points. So the first problem is inconsistent finding. So with inconsistent finding, what happens? I talked about you have in the whole SDLC, you need to make sure the code is secure. And different stages, if you are running different tools, they can provide different inconsistent findings. I will talk more about the detail how we are solving that problem, but let's first understand how our SAST engine works. So what we have done in AWS, we have built one single SAST code scanning engine, which supports code scanning for code security and also code quality issues, whether it is AWS best practices or ML best practices. Or so all those findings we detect. We have over 2000 detection rules for all these different categories of detections. We support 10 programming language, and we are very rapidly adding more programming language based on our customer need. The second thing is, the security issues could be related to your hard-coded credential. You may have in your code or your text file, in config, you may have your secrets. And there is always a risk you can deploy this secrets into your application, or maybe you can commit into your GitHub repo, where it can be accessed by many developers. So to prevent that, what we have done, we have integrated the secret scan also into our our code scanning engine, so that you don't have to install some other tool to run the secret scan. Another thing which we have seen, one of the best practices for software development is you should deploy your software through the code, mean infrastructure as a code. When we hard-coded many of these resources into config file, and when we rely on the config files, then many times when we do the deployment, it becomes very difficult. So it is always better we deploy the software stack and the changes into software stack through the code. And there we have CloudFormation, Terraform, CDK. There are many different frameworks are there. So what we have done, we have also integrated the ISC or infrastructure as a code scanning into our code scanning engine. So that one-stop shop, once you have this engine, it can help you to detect issues in all different use cases. We cover OWASP top 10 vulnerabilities, and also we cover the CV20 top 25 vulnerabilities as part of our detection. Now, coming back to our CI/CD pipeline, where for different stages, I have shown you, like, we have Amazon Q Developer for ID, Code Guru Security for CI/CD and code pipeline, and you have Amazon Inspector for the monitoring your production application. Now, if you suppose you have a developer who is writing code in the ID, and suppose you have CI/CD rule where if you have a critical vulnerability, your pipeline will get blocked, or you will not be able to merge your code. In the ID, if you have resolved all the critical and high vulnerability, then you want to be sure that your changes will go through and it will not get blocked into your pipeline. And that's where the consistency becomes important. To make sure that we generate consistent finding across all these different tools, we have integrated this code scan engine with all the SAST products which we have in the AWS for different use cases. This helps you to get the consistent finding across different stages of your SDLC. The second pinpoint is the high false positive. What is false positive? False positive is where a tool, SST scanner, tells you that, hey, there is a security vulnerability at a particular line number in the code, but actually your security engineers or developers will feel that, hey, this particular finding is not going to make my code insecure. Let's take an example. We have MD5 algorithm for many people use this for encryption, and many developers use this for generating unique IDs. So if you have a MD5 API used in your code, and if the SAST scanner goes and detects every instance of MD5 and start flagging that, hey, there is a security risk, it is not correct. If you are using MD5 for your encryption, then it is a security vulnerability. But if you are just using MD5 for the unique ID generation, you are fine. So it is very important we look into the context of the code, and based on that we mark whether a use of an API or a code has security vulnerability or not. Apart from that, what we do, we use a test-driven approach for building the detection rules. We start with gathering the compliant and non-compliant samples for every security vulnerability. Then we write detection rule for those. We run those detection rule over large corpus of data to generate the findings. And I want to clarify that when we talk about the data, I'm referring to the public data and our internal code. We don't use any customer code for our model training. And once we get the detection, those detections, we do the shadow review. Shadow review is the process where we look into the detection and we check whether the finding is correct or not, whether it is having false positive or not. And we do the shadow review using the manual approach, like we manually review, and also we use LLMs and generative AI also to assist us with the shadow reviews. We have some automation in place for that. Based on the shadow review finding, we refine the rule. We deploy the rule for the beta testing. From beta testing, we gather the false positive and all this developers' feedback we collect, and based on that, we update the rule. So this whole cycle always keeps running, and this helps us to keep the false positive at very low. All this detection rule we deploy at scale for all Amazon developers, and there also that is another source where we get a lot of findings from them. And we work with all the developers to fix those. Now the third main point is the lack of developer friendly tool. So what happens that many of these SAST scanners are built from security engineer persona who are deep into this security scanning or application security business, they understand that. So even if they get a tool which is not so much developer friendly, it works for security engineers because that is the primary part of their job. But for developers, it becomes very difficult. They have to go learn some tool, they have to install it, they have to understand what those findings are. So there is a learning cycle involved here when developers get to do need to write the secure code. So to solve that pain point, what we have done, we have added security scanning feature as an inbuilt feature in the Amazon Q Developer. So when you use Amazon Q Developer, you get the security scanner. You don't have to install any software or any third-party tool. And when you code in the ID, when developers code in the ID, there only they can run the security scan. If you run the project scan, what we do, we take the all code in your workspace, whether it is your code, programming language related code, whether it is config file or whether it is your text file which could have hard-coded credentials. And we run code scanning, IC scanning, secret scanning, everything within the ID, and we give the findings and the recommendation how you can mitigate those issues. Another one, the pain point was the context switch. So we talked to developers and to our customers, and we asked, hey, what should be the best way for running this security scan? And developers said maybe the best will be if I don't have to run the security scan. When they write the code, you use many type of linter. Developers use linters, and linters look into the issues while you are coding, and you don't have to take any manual action to get the linter finding, and you see the detection as you code. So what we have done, and this helps you to not context switch. When you are coding, you don't have to take any action to get a linter finding. So what we have done, we have added an auto scan feature in the Q developer, where it keeps monitoring when you are developing the code. This auto scan feature keeps monitoring your code, and it automatically runs the scan. And it shows you the finding, and you will see this yellow squiggly line in your editor. If you don't want to do anything, just keep moving, keep writing code. But if you want to look into are you introducing any security vulnerability or something, you can click that, and you can look into the detail, and you can learn about what the issue is, and then you can fix it while you are coding. So this approach does not require any context switch for the developer. The second thing is, when we give the finding, many times maybe developers want to learn more about the issue. Maybe they have some follow-up question, or maybe they need some more detail, or maybe they are looking for some alternate ways which they are familiar to solve that particular issue. And for that, typically what developers do, they take that finding, they copy that detail, and they go and paste into their favorite some tool, whether it is a QID chat or whether it is Google somewhere. You have to put that code, and then you ask questions. To automate this whole process, what we have done, we have added a feature where along with the finding, you get an explain option. You click on that, and that finding automatically gets open into Q chat, in the QID chat, where we show you much more detail about what the issue is and how you can remediate that. And if developers have follow-up question, they can ask there. So this option helps developer in reducing the context switch. The next pain point is lack of domain knowledge. So we talked about safety-led security approach, where we want developers to take care of the code security issue while they are building the application. But developers may not be familiar with the security domain. They may not know the best practices. So what we have done, and generally how the process looks like, developers get the finding, they get the detail about the finding, and then they make the code changes based on the recommendation. Sometimes they have to go and look into some of the wikis or some of the documentation. Once they make the code change, they have to get the code reviewed, and then they have to work with their security engineer sometime to make sure the fix which they have added is correct. So this whole cycle takes a lot of time. So to reduce that pain point, we have added an auto fix feature in the ID. So when we give you the finding, we also give you the code patch. And here we use generative AI technologies to generate these code patches. We have both rule-based and LLM-based solutions. And along with the finding, you get code patch, and you can apply that code patch in your ID with one click. This saves a lot of time for developers because all those research work they don't have to do. Today we support auto fix feature for 5 programming languages, and by end of this year we are planning to extend to all the languages for which we support the detection. The last pain point is insecure code generated by the AI. Like I talked about, like developers are relying on the AI tools. I mean, AI is helping as a coding companion and generating a lot of code, but many times AI can hallucinate and it can generate insecure code. And now developers have additional burden where they have to make sure that the code which they are writing is secure, but also the code which is AI generating is also secure. So let's talk about how, in general, AI tool or AI code companion generate the code. So it starts with the training process. We collect lot of data, public data, and then we train the model, train the large language model. Then that model we host on a hosting platform like Amazon Bedrock. Then we build apps which actually talks to the LLM model, and customer sends the input to the Amazon Q Developer app or any other app. App forward the request to the model, model generates the response, and the response goes back to the code fixes and all goes back to the developer. This is a very simple view of this. There are a lot of other stages which happens. But here we identify a couple of ways where we can make the code generation from AI secure. The first thing what we have done, we added security scanning in the data ingestion process itself. When the data is getting ingested, we run the security scan, we filter the code which has high and critical vulnerability, and we train the model using the filtered secure code. This step by default reduces the security vulnerability from the AI output significantly. The second thing what we do, when the model is generating the output, we have many input and output guardrail which I am not showing here, but one of the guardrail which we have added is the security scan. So when the model is generating the code, we run the security scan, and if suppose for inline completion you are getting multiple findings, some of the findings which may be insecure, we will just prune it. You will not even, the developer will not see those findings. And for certain other finding, we will use auto fix feature, and we fix the code snippet, and we send the secure code back to the developer. So this way developers can confidently use our AI coding tools and can be sure that the Q developer is generating the secure code. Now I will hand over to Pranav, my colleague, and who will walk you through the code scanning engine. Thank you.
Okay, thanks Chandan. Hi everyone, I'm Pranav. I'm the science lead of Q Security Analysis, and today I'll dive deep into the code scanning engine. Okay, so let's dive into it. So let's start with a high-level overview of the architecture of the code scanning engine, and I'll walk you through the workflow of code scanning. So the workflow starts with the developer requesting a security scan. The request for the security scan goes to the Q Developer plugin in the IDE. The plugin would upload the code artifacts to the S3 bucket and also send a request to the backend engine to start a scan. The backend engine would download the code and would pass the downloaded code through a combination of rule and ML-based filters. These filters identify 3P code, for instance, all the library code that is in the code artifacts, and pass the first-party code to the code partitioning engine. So we'll dive into the code partitioning engine in the next slide, but at a high level, this engine partitions the code artifacts into smaller independent chunks of code that can be analyzed independently by the detectors that are powering the security analysis. Each of these detectors generates findings if your code is insecure, And these findings are aggregated and they are forwarded to the code fix generator. Again, code fix generator is a component that we will peek into in the latter part of my slides. But at a high level, it takes all the findings that are generated by the detectors. It generates the fixes for those findings, and both the findings and the fixes are aggregated and sent back to the backend engine. The backend engine surfaces these generations, both the findings as well as the fixes, to the user through the plugin. And finally, the code artifacts that were uploaded in the S3 bucket, they are deleted. So having understood this very high-level architecture of the code scanning engine, we'll focus, or rather peek a little bit into three components. So we'll look into the code partitioning engine, we'll look into the detectors that are powering the security analysis. In particular, we'll look into the program representations that are the foundations of these detectors. And finally, we'll look into the code fix generator. Okay, so let's start with the code partitioning. So code partitioning is extremely crucial when one is analyzing large repositories or whole applications. Most of the analysis algorithms for code analysis are either quadratic or cubic in time complexity. And so when analyzing large applications, the analysis of the code can take a long time. Possibly it can also lead to timeouts. The goal of the code partitioning engine is to break down your application code into smaller independent chunks that can be analyzed independently in parallel. And this way, the memory footprint, the analysis time can significantly be reduced, while the partitioning algorithm ensures that this does not come at the cost of the accuracy or the quality of the findings. Now, this trade-off between the analysis time or the memory footprint on one hand and the quality of the findings is very effectively managed in our code partitioning engine through a new partitioning algorithm that we've developed. This partitioning algorithm, it starts by mapping all the code artifacts, including the files or the classes. It maps them to different partitions, and then incrementally it combines the partitions that have a high code cohesion. In this way, the partition that we obtain at the end of our analysis includes code artifacts that are dependent on each other into the same partition, whereas artifacts that are independent of each other, they can be analyzed in parallel. They're mapped to different partitions. So this is a very, very high level kind of overview of the partitioning algorithm. If you are interested to learn more about the details, please take a look at the paper that we submitted on this algorithm, and it appeared in the Foundations of Software Engineering in 2022. Okay, so coming back to this overview slide, we've looked into the code partitioning algorithm at a high level. Let's now look into the detectors that power Q security analysis. And in particular, we'll look into the implementation of the detectors that are the foundations of this analysis. Okay, so all the detectors that we've developed, a lot of them are based on the mu graph program representation. The mu graph representation is a very rich internal program representation that is obtained from source code. And to learn more about the mu graph representation, let's use this running example. So this is an example method, create SQL connection, where the developer is creating a SQL connection. And they're doing that by calling the getConnection API that is declared in the driver manager class. The thing to note here, though, is that the developer has hard-coded both the username and the password in the code. And as you would understand, this is a critical security vulnerability. As soon as this code is checked into the repository, an attacker can gain access to these credentials and can use this to access the SQL database without authorization. Now, to detect such vulnerabilities, the code scanning engine converts the code that is on the left side of the screen into a representation, a graph representation on the right side of the screen. And this representation is called the mu graph representation. This representation, as I've already hinted, is a graph data structure comprising of nodes and edges. The nodes correspond to different code entities. For instance, so for instance, the get connection node that is present in that graph, it corresponds to the get connection API defined in the code. Then there is a return statement at the end of the graph in the bottom right. It corresponds to the return statement at the node. And similarly, there are nodes that correspond to data objects. So you have a node that corresponds to the password for the username. There is a node for the connection object. And besides these node entities, there are also edges that are connecting these nodes, and those edges correspond to the dependencies. So technically, the mu graph representation is what we would call a program dependence graph. And this representation very precisely captures both the data and the control flow in your program. As an example of data flow, we can look at the edges that are incoming to the connection object in the graph in the right. And we see that there is an incoming definition edge to this connection object, which indicates that this object is obtained by the value that is returned by the get connection API. On the same lines, there is an outgoing parameter edge that is connecting this connection object to the return action in the graph representation, which is an indication that the return statement in this method is actually returning this connection object. If you want to learn, if you want to look at the control flow in this graph, you can see the dependence edges that are connecting the compute connection string, the method at the top, to the get connection API. And similarly, there is a dependence edge that connects the get connection API to the return statement. And these dependence edges are indicating that as the program executes, we'll first execute the get connection string method, followed by an execution of the get connection API, followed by an execution of the return statement. Okay, so as we'll kind of see very shortly, the graph representation is precisely tracking the data and the flow of control in the program, and tracking these is extremely crucial for being able to express the security vulnerabilities that we want to check in our code. Besides being able to track these control and data dependencies, there are several other salient aspects of the mu graph representation. One salient aspect is that the representation captures the semantics of the programs and not its syntax. So let's look into this code example. Again, it's a very small tweak on the example that we see before. In this example, the developer is storing the output of the URL that is returned by the compute connection string method into a named variable. It's a very small difference, but by using a named variable, the syntax of the method is completely kind of changed. It's very different. But in terms of the semantics, there is no behavioral change. So when we look at the graph representation of this code, it's exactly the same as the representation of the previous method. And so by enforcing, or rather by checking properties on top of this graph representation, we are ensured that the detectors that we built will be robust to these syntactic variations and will be checking the semantics of the code for security vulnerabilities, and not just and will not be flagging these vulnerabilities based on purely the syntax of the code. And finally, the mu graph representation includes analyses such as type inference, constant propagation. So as an example of type inference, you can look at all the data objects in the graph representation of the code. All of them are typed. So you see that the password and the username are of string type. The connection object corresponds to the Java SQL connection class. It has the connection type. And the vulnerability in this code is based on the fact that the password that was passed as an argument to the get connection API is a hard-coded string literal. It's a constant string. And this is again something that we get in this graph representation using the constant propagation semantic analyses that is that's powering this representation. So putting all these salient aspects of the mu graph representation together, we have looked into the fact that this representation is robust to syntactic variations in code. We have seen examples of semantic analyses such as types and constant propagation that are making this representation very rich. We have also seen how this representation is precisely tracking data in control flow. And putting all of these things together is important to being able to precisely express the security checks that we want to enforce in our code and that we want to use for checking vulnerabilities in our code. So we've already discussed the fact that the code on the left is insecure. It has a critical security vulnerability. The root cause of that insecurity is the fact that the developer is calling the get connection API and it's passing a hard-coded string as the password when making that call. Now, expressing such checks on top of the mu graphs is enabled using the Guru query language that we have developed within our product. This language, the Guru query language, or GQL, is a domain-specific language which can be used to express checks such as the one that is described on top of mu graphs. And for the hard-coded database credential leak, the check that we've discussed, the GQL detector corresponds to the following snippet, largely corresponds to the following snippet. So in this detector, the detection first checks for the existence of a get connection API call in the program. We want to make sure that it's not just any other get connection call, it's the one that is declared in the Java SQL driver manager class. We want to further make sure that there are 3 arguments that are passed to this call. So we are not spuriously raising false alarms if the developer is using a different overload of this method. And finally, we check that the 3rd argument, which corresponds to the password, is a hard-coded string literal. Okay, so as you can see, there is a lot of context that is going into this check. And further, this check is using a lot of the semantic information like types and constant propagation, data and control flow tracking that we've discussed before, that is present in the mu graph representation. Okay, so we've looked into the code partitioning. We've seen the mu graph representation and how it is used to write very expressive, rich detectors. Let's now look into the autofix generator that we have developed using generative AI. So autofix generation is a generative AI offering for fixing the security vulnerabilities that we find in the code. And this feature is a combination of rule-based fixes, which is a library of code transformations over the abstract syntax tree of the program, and an LLM-based fix, which is powered by a first-party large language model that is fine-tuned on bug-fixed paired data set. And using a combination of both the rule-based and the LLM-based fixes, we power the autofix generator, which a user can realize in their IDE using in the manner I've kind of shown in the screenshot here. Right. So when the user finds a security issue in their code, the autofix generation will populate a fix suggestion in the description of the finding. In the running example that we have discussed before, the fix is to suggest the user to replace the password with the code that reads the password from the environment variables, from the system environment variables. And the user, if decides to accept this recommendation, they could click on the fix button on the fix feature, and clicking on that fix would apply that code patch in their code, and in this way remediate the vulnerability. Okay, so we've dive deep into the three components that I talked about: the code partitioning. We looked into the detectors that are powering the security scan, and then we looked into the autofix generator that the users or the developers can use to fix the code if their code has security vulnerabilities. Let's now very quickly go into a live demo. This is a recorded demo where I walk through the running example and show how the developer can use the security scan feature in QDeveloper IDE plugin to help write secure code.
Hello everyone. So today I'm going to demonstrate the security scan feature in Amazon Q. For this demonstration, I'll use a running example that we have already seen in our presentation. So this is a simple Java code that the developer is writing to connect to a SQL database. In particular, let's assume that the developer is written this method create SQL connection to create a connection to the SQL database. So let me very quickly copy the code that we've already seen in our presentation before. So in this code, we see that the developer is using the driver manager class to create a connection, and they pass to the get connection method a URL, the username, and the password. As we previously discussed, the developer is hard-coded a password in their code. This is a critical vulnerability because as soon as the developer checks this code and merges it with the main line, a malicious actor can use the username and the password to connect to the SQL database in an unauthorized manner. The developer has Amazon Q running in their IDE, and they also have the autoscans feature on, which means that Amazon Q is proactively scanning their open file for vulnerabilities in their code as they are developing their code. In this particular example, Amazon Q finds the hard-coded password vulnerability that they have introduced in their code. The developer can hover over this vulnerability to understand the vulnerability in more detail and also see a fix preview that would fix this vulnerability. The developer can click View Details that would open a tab in their IDE with additional details about the vulnerability. It also has links to the Common Weakness Enumeration or CWE that corresponds to this vulnerability, and links to the hard-coded credentials and the fix preview. The developer can click Explain that would share the vulnerability along with the code context with QChat, and the QChat will generate a response that describes the vulnerability along with a potential fix. And finally, the developer can click Fix that would apply this suggested patch in their code, and with this also fix the vulnerability that existed in their code. Okay, let me quickly go over the second example. This is an example for scanning infrastructure as code. In this example, the developer is creating an S3 stack using the CDK in Python language. In particular, they've written this method create S3 bucket to create a bucket of the given name and return it. We know that S3 by default does not enable SSL TLS encryption for data in transit, and creating the bucket using the default configurations leaves this bucket vulnerable to interceptions. Amazon Q Autoscans is enabled in the IDE for the developer. Amazon Q identifies this vulnerability as the developer has written this code. The developer can hover over the vulnerability to read more about this issue and also see the fix that would fix this issue. In this case, the fix is to enforce SSL as the bucket is created. The developer agrees to this remediation and clicks Fix to apply this fix in their code. There are actually two vulnerabilities in this code. The second vulnerability is about the lack of encryption at rest, and as described in this description, the developer can get rid of this vulnerability by enabling KMS encryption. Okay, so we have seen two examples in this short demo about how the security scanning feature in Amazon Q can be used by the developers to detect and remediate vulnerabilities. The first example we saw about scanning Java code, and the second example was about scanning infrastructure as code. And in both the examples, Amazon Q helped the developer find vulnerabilities in their code while they were writing the code without any change in the context, and also help them remediate the vulnerabilities even if they lacked the required security domain knowledge for doing that.
Okay, so that was the demo. That's it from us. Thank you very much. Thanks.